Okay, hi everyone. So welcome to my workshop. I'll be talking about trigonometry in more celestial and astronomy-based contexts today. So for instance, we're going to attempt to use trigonometry to find a few distances that may be larger than what you might think you can find, like maybe the Earth's radius and also the distance from the Earth to the moon. And first off, this is only about the 10th or so workshop that we have lined up in our Fun Math Workshop series here at LogiSTEM. There are 6 more topics that are really quite interesting, and I encourage everyone here, if they do have time, to check them out. Also, if you do find any of the previous topics interesting, all available recordings are posted on LogiSTEM's YouTube channel, which can be found if you just search LogiSTEM in YouTube. But for now, let's just get started. Okay, so first off, in case anyone is unfamiliar with trigonometry, I will be going over kind of the basics. As a disclaimer, it is helpful if you do have some geometry knowledge as well in the later problems. But first, I have here written that there's a common acronym you'll encounter, and the pronunciation is not really important, but I will be referring to it as SOHCAHTOA. So SOHCAHTOA represents 3 of the most important trigonometric basic functions: sine, cosine, and tangent. And it's basically an acronym to help remember what each of the functions are and how you can find them too. So first, we come across the first 3 letters, SOH. And of course, we have sine, and this part just basically means that the sine of angle x is equal to the opposite length over the hypotenuse. So here, since we have angle x, this would be the opposite length because it's opposite of the angle. And since we are dealing with right triangles in trigonometry for the most part, this is the hypotenuse. And basically, to find the sine of this angle, you just divide this length over this length. And next, we move on to the next 3 letters, CAH. And these represent, as I have written, cosine, adjacent, and hypotenuse. And what this one means is very similar. So you have angle x, and how you find the cosine of angle x is, the adjacent length. So basically the side that is adjacent to the angle that is not the hypotenuse, and then divided over the hypotenuse. And finally, we move on to our last basic trigonometric function, tangent. And TOA represents tangent, opposite, adjacent. And this one just basically means the tangent of angle x is equal to the opposite length divided by the adjacent length. So that is kind of the basic. Again, if you don't really completely grasp this concept yet, it is totally fine. What I will be going over in our next couple of problems are more about concept. And if you do have any questions though, feel free to either message me privately or just put it in the chat if you have any questions. But if not, then we can move on. Okay, and it might be helpful to screenshot this slide or at least this part for the next slide we will be going over, which is kind of a basic exercise using this acronym. Okay, so now let's just move on though. Okay, so for some quick practice, I have 3 problems listed. Be careful of which ones I'm referring to. I did not put them in order with the acronym, but the acronym is here if anyone wants to refer back to it. And if you have any answers, feel free to send them to me, and then I will go over them in about 3 or 4 minutes, depending on how many answers I get and kind of at like what speed. Okay, yeah, so I've received several answers, both in the public chat and also in the private. And everyone who sent me an answer got it correct, so congratulations. For people who don't really get this concept yet, I'll kind of just do a basic walkthrough of all three, and then we can get on to the more interesting problems. So first, we want to find the cosine of x using this diagram. And referring back to our acronym, we have CAH, and this represents adjacent over hypotenuse. And so the adjacent side to angle x is 4, and the hypotenuse of this triangle is 5. So the cosine of x is just 4 over 5. Also, if you are joining, please mute yourself if you're new. Also, we can move on to the next problem. So the sine of x using this diagram is, first we see that the sine is the opposite length over the hypotenuse. And the opposite length across from angle x is 8, and the hypotenuse of this triangle is 17. So we can also just say that the sine of x is 8 over 17. And for the last problem, we want to find the tangent of x. So we want to find the opposite length over the adjacent length. And the opposite in this case is 9, and the adjacent length is 40. So once again, just congratulations to everyone who got it right, especially if you're learning this for the first time, because that's actually pretty quick to pick up. But for now, let's move on unless anyone has any questions. Okay, so for this next part, you may want to grab a calculator with trigonometric functions if you do feel a bit more comfortable with these concepts. If not, that's totally fine as well. You don't need to calculate everything as long as you get kind of like the basic idea of what's going on. Consider yourself successful in this workshop. But yeah, okay, so I'll wait for about 30 seconds or so if you do want to grab a calculator, and then we can move on to the first problem. Okay, so now moving on. Here is some historical background on the first problem that we will be kind of really attempting. So Abu Rayhan al-Biruni was an 11th century mathematician who was located in Persia, more specifically in modern day Pakistan, if you're interested. And using simple trigonometry, he managed to use the size of a nearby mountain he found to then find the radius of the Earth. And of course, while this wasn't exact, he did manage to find a pretty close figure that is actually within 1% of Earth's actual radius. And obviously there weren't cameras around back then, so this is a rendering of what he probably looked like at the time. And now we'll just move on to our first problem. Okay, so first, as you may recall, I said that he used the height of a nearby mountain. And while no one could really find what exact mountain he used, as names have changed throughout history, the overall process was that he used a square board or cube of about 1 meters in all dimensions, which is also 100 centimeters, since we will be switching between both measurements. So he lined up BC visually with the top of the mountain that he could see. Again, note that the diagram is not to scale because he obviously could not find a square that was actually this big to help measure the mountain. But measuring what he could he started out with the lengths AG, which he found to be 0.001648 centimeters, and also the length of CH, which was equal to 5.028 centimeters. CH was found either with the shadow, or he might have used a string to drop it down perpendicular with the help of gravity. And the rest was actually using similar triangles, which you may be able to figure out with this diagram. So obviously, I'm not asking for any exact measurements. Of course, if you can find it, that would be really impressive. But look over this diagram for a few minutes, see maybe what ideas you may find, and also maybe some ratios that might be helpful to find eventually EF, because EF represents the height of the mountain. Again, I'll probably give until 7:19 to start kind of going over this process. And once I start going over it, I'm not really going to have any more breaks until I actually end up with the height of the mountain. So that's why I am giving a bit more time. Okay, yeah. So congrats to people who did send me answers privately. You all did point out the similar triangles that we will eventually end up using, but I will start explaining now. Okay, so first we have that triangle DAG is similar to triangle ECD. So this is DAG and this is ECD. This is proof by AA similarity. So we can take from this similarity relationship, the ratio of DA over AG is equal to the ratio of EC over CD. And remember that we do know what the lengths of DA, AG, and GB technically are, just because these were like measurements that were relative to what he could find. So basically, like using a ruler, he didn't really need to do any crazy measuring. But from here, again, like I mentioned, he did know all of these lengths. So he was given 100 centimeters and these lengths, as I mentioned previously. And so writing these into a ratio, he could then simplify this to this, right? And then it's quite clear to see how we can solve for n in this case. So we can expand and then divide to get that n is equal to CE, which is then equal to this, which I won't say in centimeters just because it's a bit long, but 6,067.961165 meters, which he found to be EC. And clearly this isn't what he actually set out to find because he wants to find EF. So then we move on to our second pair of similar triangles. Okay, so next he also found, and some of you pointed out, that triangle DHC is similar to triangle CFE. And this was actually really smart because now he does know EC, and all of these measurements that he can find are mostly relative and easy to measure out. So the next ratio he pulled from this was CH over CD is equal to EF over CE. So CH over CD is equal to EF over EC, and now the end is kind of in sight. Okay, so now plugging in, once again, the values that he does know, we have this ratio. And then using the same method of cross multiplying and then dividing, we get that the height of this mountain that he used was 305.097 meters. So we are actually already done with the first part of the problem. And this was also without using trigonometry. Okay, so the next part does get significantly more complicated, but I will explain it to the best of my ability. So from here, he used basically this small measurement, which he knew because this entire triangle kind of represents the height of the mountain. And once again, this diagram is not to scale either, because if it were to scale, you probably wouldn't even be able to see this cube, or the Earth's surface would have seemed flat, which kind of defeats the purpose of what we're trying to find. So from here, just to kind of simplify his methods, we are given that 0.5833 degrees is the dip angle. So the triangle's angle is 90 minus this, because what a dip angle is basically if you were looking across, like straight across from the top of the mountain, then you would kind of have this line. Of course, it doesn't look exactly perpendicular right now just because of the curvature of the Earth, but once again, this mountain is very small in comparison to the surface of the Earth. So that's why we can just take that the triangle's angle is 90 minus this little dip angle over here. So now this is kind of where trigonometry comes in. I will be explaining my other diagrams as well, but we have this basic equation of the sine of this triangle you can see here. So the sine of this angle is equal to, like we said before, the opposite over the hypotenuse, or this length over this length. So, okay, going back to explaining what these diagrams are in case it's a bit difficult to follow. This is kind of the main diagram that we are working off of. But in a larger context, obviously this one isn't the most accurate either. I did try to copy paste the diagram we used from earlier to try to make it a bit more comfortable or suitable to understand. So this is basically the context of the Earth as a whole, while this is just a small part of it enlarged. And to make our calculations easier, this triangle here, which we can see, is kind of formed by the line from earlier, so EC, as well as the Earth's radius. So this is the center of the Earth, assuming, and we pull out this triangle to kind of get this, which is really what we're working with. Again, we're not really taking into too much account the actual curvature of the Earth, just because the mountain is very, very insignificant in compared to the Earth. So basically, if you were walking across the room, you wouldn't really be thinking about the curvature of the Earth. And that's kind of why he was able to do this, and also why his measurements aren't exact. Okay, so now that we have this equation, oh no. Okay, so we can expand out this equation because we do want to find r, since r is the Earth's radius. So we can expand it out, and solving for r, we can first distribute these to both of the values here. So this is kind of what we have, which is equal to r from earlier. And then moving this term to the other side and then factoring out the r, so that we kind of just have the one, like the single term r. We have this. So this is basically the right side of the other equation, which is equal to this again, which is from here. And then at last dividing this kind of term that is currently attached to the r, we have that r is equal to negative sine of that big angle that we found earlier times the height of the mountain over this term from earlier, which ends up going to about 5,887 kilometers. And if you want or are curious, you can look up the Earth's radius now. Earth isn't a perfect sphere, so there is like a mean radius that's generally considered by scientists, but I will be showing what the actual radius is at the end of this workshop if you don't want to, so stay tuned. But now we can move on to our next problem, since we technically already found the Earth's radius. Okay, so again, with some historical context, this next problem was solved by Hipparchus, who was an ancient Greek astronomer and mathematician. Actually, his background as an astronomer does come into play in this next problem, since I won't fully be able to explain where all of his information came from, since some of it did come from astronomy, and I'm not particularly well versed in astronomy. But he was alive in like around 200 years before Christ, and he is thought of technically as the founder of trigonometry, because he was found to have compiled an early example of the trigonometric tables. So like what the values of like sine of 3 degrees and such were. But for this next problem, he is actually also known to have measured the distance from the Earth to the moon pretty accurately, actually, within 1% using his discovery of trigonometry. Okay, so this problem, again, is very heavily based off of astronomy. So I will, for the most part, be explaining it more with words. I think the main point to get from this problem is more so just the concept. But okay, so as an astronomer, he had figured out that there would be a full eclipse at Hellespont. And since different places will experience different kind of versions of the eclipse, there would also be a partial eclipse at Alexandria. And he also estimated with this knowledge somehow that there was an angular width of about 0.5 degrees. And what the angular width kind of is like this right here, this angle. And he focused on point E, which represents the edge of the moon in what he could see. And note that this point does overlap with D during the solar eclipse at Hellespont because it's a full eclipse and the moon will fully cover the sun. And from Alexandria, since it was a partial eclipse, it would overlap with point C at the sun. Again, this problem is a bit more difficult to conceptually understand. So if you do have any questions, feel free to send them to me. But hopefully everyone does get this first part, as it does get a bit more complicated moving forward. But okay, so now he denoted X as the fraction of the moon that was visible. So this was basically like during the partial eclipse, because obviously during the full eclipse, he can't see the moon. But X covered an angle of 0.5x in the sky. So that was just like kind of this area. And knowing the latitudes of Hellespont and Alexandria, I will explain latitude briefly since it's related to geography. But if you've seen in maps, like the vertical lines that kind of run across the maps, that's basically the latitude measures. So for instance, at the equator, it has a latitude of 0, I believe. And it kind of just goes outward from there. So from the top to the bottom, it will have positive and negative latitudes. But previously, he did know these latitudes. So he figured out that AB would be this distance, which he knows because it's the distance between Hellespont and Alexandria, which is basically just subtracting the latitudes, which is then equal to 2 pi r and then times this kind of collection of symbols over 360, where this is the difference in latitude between Hellespont and Alexandria. And also r is the radius of the Earth in this case. And actually, since you might be confused where r comes from, Hipparchus was also someone who was able to figure out the radius of the Earth quite early on, since he was around in 200 BC or so. But he did have slightly more complicated ways of going about this, which is why Al-Biruni's method is a lot more accessible and understandable. But I will probably just like sit on the slide for about 20 more seconds, just so you can read over it in case there's anything you're confused by. And again, you can ask me any questions if you have them. Okay, so if there are no questions really with this, okay, so now we denote again r as the distance to the moon. And of course, this r is different from the last r we used in the other problem. So then we also had, or can write, that AB is equal to 2 pi capital R times 0.5x, which again is the fraction of the sun that covers whatever degrees in the sky over 360. So then he found this kind of like deciding ratio of capital R over small r. So the distance of from the Earth to the moon over Earth's radius was this kind of thing we see here. And remember that all of the orange variables are things that he knew beforehand, either with his knowledge of astronomy, or for instance, with this case, knowing the latitudes of Hellespont and Alexandria. So he kind of had this, and again, we don't really understand how he knew these latitudes, but he did record them pretty accurately. Okay, so now we have a distance and a relationship between the distance to the moon and the radius of the Earth, which he found using his own methods. And of course, he had a different measurement for the radius of the Earth than Al-Biruni did, since they were in different places at different times. But he found that this relationship was 69, which meant that the distance to the moon was 69 times the Earth's radius. So then using the radius that we found from earlier, since this is just a bit more relatable, then he found the distance to technically be this crazy number. So this was just 5,887 times 69, which ends up going to 406,203 kilometers. Okay, so that's actually his calculations for the distance to the moon. So we've actually covered the two main problems of today, just because these problems are a bit more difficult to understand conceptually. But I did mention earlier that we would be going over the distances that Al-Biruni and Hipparchus found versus the actual distances that scientists found in modern times. So using more like accurate instruments instead of just approximations. We won't be able to learn how to calculate the distance of stars in parsecs. But if that is something you are interested in, there's a lot of resources out there actually where you would be able to. But in like older times, it was more common to use like astronomical events. So like an eclipse, which Hipparchus used to kind of figure out how to find these distances using quite basic knowledge. So like trigonometry and again, from earlier similar triangles. But yeah, so stars and parsecs do require more like scientific knowledge and modern day knowledge, which is more so done with like technology. But yeah, I'm sure there are definitely places out there where you can find out this knowledge for yourself. But for now, moving on to one of our final slides for today. Okay, so we found from earlier that the Earth's radius was 5,887 kilometers using Al-Biruni's methods, and the actual distance was 6,371 kilometers. And this does, I suppose, from like a glance seem pretty far off, but keep in mind that I'm sure even with like people now, if you were just to look at the ground beneath your feet and be able to guess or even try to guess the distance to the Earth's core, it would not be this exact. So it is pretty impressive that so early on, Al-Biruni was able to approximate this distance and be only around 500 or so kilometers off. And from Hipparchus's methods, we found the distance from the Earth to the moon. So this one is a bit more off just because we used Al-Biruni's radius instead of Hipparchus's radius for the Earth. But he was actually a bit closer, but just for today's context, we found it to be 406,203 kilometers and the actual distance is 384,400 kilometers. Again, all of these measurements are a bit off just because if this is new knowledge for you, the Earth is not, again, fully a sphere, and also the moon is moving slowly away from the Earth just because of orbits and things like that. But yeah, again, this does seem a bit off at first. But again, this was more than 2,000 years ago. And it's also very difficult to just kind of look at an object kind of floating in the sky and be able to know that, especially since this was also before people even generally accepted that the Earth revolved around the sun instead of everything else revolving around the Earth. So all of this is pretty impressive for such like ancient times. And yeah, that kind of concludes the workshop for today. Thank you for listening, and also thank you for the active participation in the private chat. It was really nice to be able to kind of gauge where people are throughout my workshop. But yeah, that's all for today. If you have any questions or anything, feel free to stick around after. I'll be here probably until about 7:45 or 7 for just like a few more minutes. But yeah, that's all for today. So if you do want to leave, feel free to. And yeah, thank you and have a nice day. Yeah, so I don't believe I can actually end this meeting since I don't have host capabilities. So if you want to leave at any time, that's totally fine. Yeah, I'll just stick around until most of the people I would say are gone. But yeah, thank you for everyone who attended today and listened to my presentation.